Test, test. Okay. Okay. So Martin is the team lead for web application security research at SAP, and I'm a PhD student in this team. And Martin and I are working in the field of security, and we are heavily looking into topics of web security, and especially into topics like cross-site scripting, clickjacking, cross-domain communication. So everything that happens in the browser and everything that happens with HTML5. And we do that in two projects, namely WebSend and Struce, whereas WebSend just finished. So currently we're only running Struce. And we are visiting conferences a lot, and on all the conferences there are different talks about HTML5. And on security conferences you can often see HTML5 insecurity talks, or hacking with HTML5, or new vulnerabilities in HTML5 feature X. And there's some kind of preconception that HTML5 is somehow insecure. And a lot of developers also think that. And we think that this perception is unfortunate, because HTML5 APIs are probably for the first time functionalities or new browser features that come with a very well-defined security model in mind. And to overcome this preconception of this insecurity, we created this talk. And in this talk, we would like to compare HTML5 features with their legacy counterparts. So we look at the features, check which use cases. Oh, with luck. This might work. Ah, great. No, it's off. No, does not. Oh, no. Great. So I got a laser pointer. So the goal of this talk is to compare HTML5 features with their legacy counterparts. So we would like to see how certain use cases were done before HTML5 and how they can be done with HTML5 and how the security looks like in these cases. And what we would like to do is we would like to keep score between HTML5 and the legacy features. So let's have a short look on the agenda. So in the beginning, I would like to give a short technical introduction into the topic, so explain the basic security concepts that we have in the browser and how authentication in web browsers work. And then we will have sort of an HTML5 deathmatch against legacy features. And we will have 4 rounds. So we first speak about client-side cross-domain communication. Then we will talk about in-browser communication. Then about client-side persistency. And in the end, we will talk about click checking. And in the end, we will also have a conclusion. So, but let's start at the beginning with the technical background. So if we talk about HTML5, we first need to define what HTML5 actually means, because the term has some different notions depending on who you're talking to. And here I have a good picture that shows the current state or the state of HTML5 1 year ago, and it shows basically the complete picture. So what we see here is we see certain different bubbles, and each of these bubbles is one specific technology. And if we look at this picture, we also see 3 different bigger circles. So we see the inner circle, we see an outer circle that is in blue, and we see the biggest circle in light green, I guess. And here we see what HTML5 actually is. So in the middle, so this circle here, this one, this shows the initial HTML5 specification that was created by the Web Hypertext Application Technology Working Group. This specification was then handed over to the W3C, which slightly extended this version. And if we are talking about HTML5 strictly, we normally need to stick to this set of technologies in the middle of here. And then we have the outer circle, and the outer circle contains a lot of different technologies that are not belonging to the HTML5 specifications, but are somehow related to HTML5. And most of the people who speak about HTML5 actually mean the whole picture. So HTML5 is just a buzzword for all the new technologies that are coming into the browser. So everything that is new and that offers an API or enhances the browser's functionalities is called HTML5. And in this talk, we would like to stick to this term. So we would like to see HTML5 as a buzzword that contains all the new technology and not only the things that are covered in the core specification. Before we start with the technical things, we first need to introduce how security in web browsers work. And the most basic thing that we need to explain is the basic web application paradigm and how authentication in such a paradigm works. So in general, in the web, we have two entities, the client and the server. And the server is some host on the internet that has a domain name associated with it. So here, example.org, and the client comes in the form of a browser. And the browser, if the user wants to visit a certain website, he specifies the URL and presses enter, and then the browser sends an HTTP request, the server processes it, returns an HTTP response, and the browser renders HTML. That's pretty easy. And now authentication comes into play. So if we would like to create sophisticated web application, we need some form of login or state tracking in the browser. And this state tracking happens implicitly. So the browser manages all the authentication state for us. So in the beginning, we always have some initialization phase. So for example, we go to a website, we register at a website, and then we log in. And upon the login, we receive some authentication credentials. And these authentication credentials could for example, be a session cookie, could be a HTTP basic authentication credential, or it could be a client-side SSL certificate. And as soon as we have established a session with the website and authenticated ourselves, the browser manages everything. So the browser automatically attaches authentication credentials to all the requests that target a certain website. So if we are registered at example.org and logged into example.org, the browser will always attach cookies to all HTTP requests that leave the browser and target example.org. And this is very important, and this has a lot of implications for security, because we need to think about the case where an attacker is able to create an HTTP request within our browser. So if he is able to create an HTTP request to example.org, and the browser would attach authentication credentials to the request, and if the attacker would be able to read the response of this request, he could basically leak private data from example.org. And this is exactly the attacker model that we are talking about in this talk. So in this talk, we're talking about the web attacker, and that is not somebody that is able to execute code on your machine, but it is somebody that is able to create requests in your browser. So for example, by sending you a link via email, or by luring you onto a website that he controls or where he exploited a vulnerability. So the web attacker is able to display some content and to create HTTP requests in your browser. And on a side note, we will also talk about the network attacker. So this is an attacker that sits in the network and is able to intercept or change your network traffic. But this is only a minor thing in this presentation. So what I just said is that web browsers handle the authentication implicitly for us. And therefore, we somehow need to prevent that an attacker is able to create an HTTP request to the application and read the response. And this is what the same origin policy is for. And the same origin policy is the most basic security policy that we have implemented in modern browsers. And more specifically, the same origin policy prevents two entities communicating with each other in the browser if they are from a different origin. So only two entities that are coming from the same origin are allowed to speak to each other in the browser. And the origin is defined by the protocol, the port, and the host that is used to retrieve an object or a communicating party. So for example, a JavaScript from example.org is not allowed to talk to facebook.com and read your private messages at Facebook. And this is what the same origin policy is about. So here we see an example. So we have a document, and this document somehow would like to initiate a request, and the request goes to http://example.com/b. And in this case, we see the protocol is the same, the host is the same, and only the path component is the same, but the path component is not part of the origin. Therefore, in this case, the browser would grant access and give access to this document. Another example is here. Here we see a website from http://example.org would like to access a website on www.example.com. I said org. And in this case, we have a host mismatch. So here we have the host example.com, and here we have the host www.example.com. And therefore, the browser prevents these two sites from communicating each other. And this also hosts for different protocols and different ports. And this is the main security policy that we have, and this prevents an attacker from sending HTTP requests to another website and read this response. So from preventing evil.com to access your private Facebook messages at facebook.com. And now I would like to have a look at the case where we do not have a same origin policy. So I assume same origin policy would not exist. What could the attacker do? So what is the same origin policy for? And in this case, we assume we have a very simple example. So we have two servers, kittenpics.org, and we have a server webmail.com. And on the client side, we have a browser, and in the front of the browser, we have a user. And the user is logged into webmail.com and receives an email. And in this email, the attacker writes, well, I have a nice website for you with lots of kitten pics, so you should click on this link. And the user would click on this link and load HTML from kittenpics.org. And what he would see is very nice kitten pics, so he's very happy. But what he cannot see is a JavaScript coming also from kittenpics.org. And this JavaScript could do malicious things. So we assume the same origin policy does not exist. So this JavaScript could simply initiate a request to webmail.com. The browser would attach authentication credentials in the form of cookies, and then the response would be returned to the JavaScript, and the JavaScript could read your email and send it back to the attacker. So this is the case when we do not have the same origin policy. So what the attacker is able to do in this case, if he would not have this policy, is he could leak sensitive information. He could read your email from webmail.com, but he could also conduct state-changing actions. So for example, he could instruct webmail.com to send an email in your name. And if we take these two capabilities together, we merely end up with session hijacking capabilities. So an attacker could impersonate you and could do things in your name and read all the stuff. And therefore, it's very good that we have the same origin policy, and the same origin policy protects us from this security threat. So now let's have a look at HTML5 and the new HTML5 APIs. And if you look at them and dig a little bit into the specifications, we see that a lot of HTML5 APIs are currently weakening the same origin policy. So they create ways to work around the same origin policy. So at first, I think a lot of you would ask, so is HTML5 a bad thing? So same origin policy protects us from session hijacking capabilities for attackers, and there are HTML5 APIs that weaken this protection against this session hijacking. And well, the short answer is no, it is not bad. And the long answer is no, it is not bad, because the ways that developers used before are way worse. So we should stick to new APIs with security models created specifically to counter such attacks. And now we will see how that looks like. So now we will have a look into and compare different HTML5 and legacy features. And first, I would like to look into client-side cross-domain communication. And here, the problem is the following. So we have a developer, and the developer says, well, I would like to open up my site, would like to create an API for my site, so I would like to offer a cross-domain data sharing or data providing service. So I would like to provide data to somebody else, to another domain, and this data is somehow dependent on the authentication state. So it is important that there's some kind of user authentication involved in it. And if we look at the same origin policy forbids this case, because in the problem statement we see that it's a cross-domain data providing service. So same origin policy would say, no, this is not allowed because cross-domain, the host is different, I block such a request in the browser. And well, developers are intelligent, and they found ways to work around these restrictions in the browser. And there are basically two ways to do so, and this is JSON-P and Flash-based cross-domain requests. And we will now look into these two cases and look into the security. So let's first see what JSON-P is. So as I told you, the same origin policy manages all the communication in the browser, But there's one thing where the same origin policy does not hold, and this is HTML tags. So you, for example, you can use an iframe to frame a cross-domain resource. There, the same origin policy does not intercept this request. And you can also include cross-domain scripts. So you can open a script tag in your website and embed a cross-domain script. And JSONP uses this functionality to circumvent the same origin policy. And JSONP is basically an endpoint that creates a JavaScript for you that calls a certain method. And I have a picture here. It works in the following way. So we have a website, and this website first creates some functionality, a function. And then we see a real-world example of a script, and this script is the Flickr API. So here you say, okay, I would like to have a new script. And within this script, I provide a URL, and this URL, I hand over the name of this function, of this process JSON function. And then Flickr dynamically generates a script for me that calls this function. So this script tag loads this script at this URL and then simply executes it. And in the script, we will see a call to this function process JSON, and the parameter of this function will be given to this function. And in this way, I can get data from Flickr within my website and process it. And if we look at the security of this, there are two major security concerns that we see here. So the first thing is that you should only use JSONP for public data, because you cannot control who is the one that uses your script. So you offer such an API, you create such a service that creates a script with the JSONP in it, but you cannot control which party will include this script in its website. So it could be used by example.org, but it could also be included by evil.com. So you do not have any access control. All the data that is shared in a JSONP is basically public. And the second point, this is also very, very security critical, is you basically execute a foreign script in your website. So in this case, we executed a script coming from flickr.org within our domain. That means that we basically grant the other party to execute code in our context. And this is a very, very bad thing. But let's first look, before we compare this to HTML5, we will have a look at the second technique. And the second technique was introduced in Flash. And Flash introduced the possibilities to conduct cross-domain requests by opting out of the same origin policy. So a website is able to say, well, I don't want to be protected by the same origin policy, please share some data. And how this works, we will see now. So in the Flash case, we have two servers. One is called b.net, and the other one is c.net. And we again have a browser and a user in front of the browser. And the user visits b.com, and b.com somehow would like to consume data that is provided by c.net, and that is protected by the same origin policy. So basically via JavaScript, this is not possible. But what b.net is able to do, so the first thing that c.net has to do is to set up a policy for the Flash file. So c.net sets this policy and said, I would like to opt out of the same origin policy for b.net. So I would allow b.net to access data on my domain. And then b.net is able to include a Flash applet into its sites that is hosted by b.net and is executed in the context of b.net. And this Flash applet is able to do cross-domain requests in a secure fashion. And it does so, so if the website would like to initiate a request to b.net, the Flash plugin actually downloads the policy of c.net and checks whether b.net is contained in its policy. So it creates a request and gets the policy, checks if the policy is valid, and if b.net is allowed to conduct requests towards c.net. And if it is allowed, it will conduct the requests and attach the cookies to it. So then it can get user authenticated data from c.net. And here's how such a policy looks like. So this is a very simple cross-domain policy, and it contains two entries, basically. So it says, well, allow access from google.com and allow access from facebook.com. So in this case, the site will say, I don't want to use same origin policy for those two sites. They are allowed to send cross-domain requests to me and receive the corresponding responses. And this is a quite secure policy. The problem is here that you can do this. What you can do is you can put a wildcard into this field and say, well, I would like to grant access to all other websites on the web. And this is not really a security problem per se, because if you only host public data, this is okay. You can do that. But this is not okay, and this is a security problem if you host private data, for example, the user's name or credit card information on your website. So we were interested in this, and we conducted a study. So we were interested in how common is it that people put wildcards in their cross-domain policy files. And we crawled the top 1 million Alexa domains, and basically we found about 80,000 cross-domain policies, and about 40% of those 80,000 policies, namely 31,000 policies, contained a general wildcard. And this was related to 2.8% of all the analyzed sites. So 2.8% of all the sites on the web say we would like to opt out of the same origin policy. And this is still not a security problem per se, because if they are only hosting public data, and therefore we digged in a little bit deeper, and we have some statistics here. So here we see a graph, and on the y-axis we see the percentage of sites that actually have a policy or have a wildcard, and on the x-axis we see the Alexa rank. And what we see here in the blue curve is the number of sites that offer cross-domain policies. And what we see is that there's a huge peak at the beginning. So the more popular sites are using that heavily. And then we have a red curve here. And the red curve shows the number of policies that contain a wildcard. And what we see is that the curves are, they are rather running in parallel. So we cannot say that there's some kind, so untrustworthy sites or not so popular sites are using that more insecurely, but all of the sites are using that in the same fashion. And what we then did, we inspected these sites and tried to look for hints that there is not only public data on these domains. So what we did, we were looking for login forms on the start pages, and we also checked whether there are some session cookies in place. And we correlated this data with the other data, and these are the sites that have a wildcard policy and at the same time have some kind of login or some kind of session cookie or session data in it. And these are still a lot of sites. So 2.8% or 2.5% approximately have this. So this is a real problem. And now let's have a look at the HTML5 way of doing cross-domain requests. And the HTML5 way of doing this is cross-origin resource sharing. This is a rather new concept, and this extends the old browser's XML HTTP request object to allow cross-domain requests. And the system is very similar to the one provided by Flash. So the site that receives the request has to whitelist the site that conducts the request to access the data. But the implementation is a little bit different. So Flash uses this policy file, and CORS uses HTTP headers to conduct this. And now let's shortly compare the security. So CORS is basically the same as the Flash model. So it provides the same security guarantees, but with two differences. So CORS also allows wildcards in its policies, but the difference is, as soon as you specify a wildcard in your domain, the browser will not send any cookies to this site. So you are not able to provide a wildcard and at the same time shoot in your foot and share all your private data to the public. So if you provide a wildcard, it's totally secure. And if you only whitelist a few sites, it's also secure. This is the one major difference. And the second major difference is that you have a much finer control about the access control. So in Flash, you can only whitelist another domain to access all your data on your website. And perhaps you have a file that's called API.php that you would like to share, and you have a private profile.php that you don't like to share. You cannot easily do it. You can do it with Flash, but it's much more difficult. And in CORS, you have a much finer control about your access controls. And here's also a short slide about the usage of CORS, so how widespread is CORS, and this is already implemented. And this is a very old picture. I guess it's more than a year old. And we see in the browsers, in the current browsers, a year ago, CORS was implemented in all versions except Opera Mini. And I guess the market share of Opera Mini is not that big. Okay, so let's have a look at the score. And who thinks that the HTML5 feature is more secure than the legacy one? Only 3, 4 people? So I think so too. So I guess the first point goes to HTML5. Now let's have a look at the second round, at in-browser communication. And let's again look at the problem statement. So we have a developer, and the developer says, well, I have a website, and this website frames some other websites. And I would like to communicate with this frame. So somehow I have this website, and I would somehow exchange data. And then the same origin policy says, no, this is not allowed because this is a cross-domain resource in this frame, and I don't allow access to this frame. So you are not allowed to exchange data. And developers are intelligent, so they say, well, I do it anyways. And there are 2 different techniques that can be used to create such a use case. And this is hash identifier parsing and the window name property. So let's first talk about hash identifier parsing. This is a very obscure technique to transfer data between 2 frames that are on cross-domain, on different domains. And it works as follows. So we have a site, and this site has a frame to another domain, and it would like to communicate. And it is not able to access the content or the URL of the frame, but what it is able to do, it is able to redirect this frame to another URL. And the same holds for the frame. So the frame is able to redirect the page it is framed in. And here the hash identifiers come into play. And the hash identifiers are the things that you can see in URLs after the hash sign. And if you reload a URL where only the hash sign or only the fragment of the URL changes, there is no reload happening in the browser, but just the fragment is changed. So what the 2 sites can do is they can redirect each other to the same URL, but only with the changed hash identifier. And then listen to the hash identifier. So they just do an interval, and then every second they query the hash and see whether the hash has changed. And in this way, they can transfer information with each other. So as soon as the top frame wants to send information to the frame, it redirects the frame to another hash identifier. The frame extracts the hash, then it reloads the top frame with another identifier. The top frame extracts the information contained in the hash. So this is the first technique. And the second technique is the window name attribute. And the window name attribute is a DOM property that is somewhat strange because it's the only property in a DOM that is not protected by the same origin policy. So the window name attribute can be set across domain boundaries, and it can be read across domain boundaries. The only thing that you need is you need a window handle in your JavaScript of that window where you would like to extract the name. And if you open a site as a pop-up, or if you frame a site, you will be able to get such a window handle. So what you can do is you can set the name of the other window. The other window can extract the value, then write another value into the name, and you can extract this thing of the window name attribute. And this is, for instance, used in the Dojo framework to enable cross-domain communication in older browsers. And in these 2 technologies, we have 2 major security problems. And these are authenticity and confidentiality. So authenticity in the sense that we're not able to control who put the information there. So if a site is called and a hash identifier is passed, we are not able to tell who sent this. Is this evil.com who sent this specific hash identifier, or was it the legitimate site at example.org? And the same holds for window.name. We can simply extract the name or the value of the name attribute, but we are not able to tell who put it into the name attribute. And the second problem is confidentiality. So window name is readable across domain boundaries, and the value stays even after a navigation. So for example, if you have a site and put some confidential information into your name attribute, and then the attacker is able to redirect the same window to his site, he's able to extract the values from the name attribute. So this is very bad because information can be lost and be accessed by third parties. Now let's have a look at the HTML5 way of doing things. And the HTML5 way of cross-frame communication is the post message API. And this is a rather new API that allows the sending of messages from one frame or pop-up to the other. And this works in this case. So as soon as you have a window handle, here we can see this is the window handle, and you can simply call the post message function, then pass a message and tell the function a target origin. And this is important for security. We'll talk about this later. And then you will send this message to this window. And this window then has to listen for messages. So messages are not received automatically, but the page needs to add an event handler for the message event. And as soon as a message arrives, this handler function is called. And then here we see the handler function. And the handler function gets an event object passed to it. And this event object contains information about the origin of the message. So we can see this here. We can make a security check and say, if event.origin equals our trusted site, then we process this message, otherwise we drop it. And here we can see that the post message gives you 3 guarantees. So the first is confidentiality. And this is achieved by adding this target origin here. If you provide a target origin, for example, you would like to send a message to example.org, then you provide example.org in this case. But if the attacker, for example, managed to redirect this frame to evil.com, the browser will notice that the frame that is actually loaded, evil.com, is different from the target origin you provided. And therefore, the browser will not send the message to this frame. So therefore, we can guarantee that the message only arrives at a site that is intended to receive the message. The second property is authenticity, and authenticity is achieved by this event.origin attribute. So whenever we receive a message, we can check where it is coming from. And if this is a trusted site, we can process the message, and if it's not a trusted site, we won't process this message. And the third one is integrity, and integrity ensures that as long as we do not have cross-site scripting attackers, but then we have other problems on our domain, the message cannot be intercepted or altered by third parties. So now let's have a look at the score again, and I think this round clearly goes to the HTML5 post message API. So it's 2-0 for HTML5. So now let's talk about local persistent state. And let's have a look again at the problem statement. The developer says, well, I would like to create an application that permanently stores data on the client's computer. And then, well, this is somewhat constructed. The same origin policy says, no, this is not allowed. Files are only accessible via file URLs, and we are in HTTP, so we are not allowed to do this. And, well, developers are intelligent, so developers say, well, we do it anyways. And a technique that can be used for storing data on the client's machines are cookie hacks. And this is quite easy. So cookies are stored on the client's machine and are sent to the server at each request. But if we want to store a data on the machine, we can simply set a cookie and put our data in there. And well, this works quite well. But a problem is that cookies are very small, so you cannot put a lot of data in there. And the second thing that is not very good with cookie hacks is that you have a lot of network overhead. So if you put a cookie into a URL that is available, you send out your data over the network all the time. So let's talk about the security of cookies. And if we store data in cookies, we have to know that cookies adhere to a significantly more lax same origin policy. So they do not adhere to port, protocol, and host, but mostly only to the host. And even the host, even this is not really true. For example, if you have a cross-site scripting on a subdomain, you can access the cookies of a father domain. So cookies are not really protected by the same origin policy. And the second problem is that a network attacker could force your application to send out such a cookie containing confidential information. So let's assume you set a cookie, then a network attacker could inject a frame into your HTTP communication, could make your browser create an HTTP request to a certain URL for which the cookie was set, and then the cookie is sent over the network, and the network attacker could extract the cookie. So let's again have a look at the HTML5 way of keeping local persistent state, and this is the web storage API. And this is a new API that is provided to JavaScript, and this API allows you to store key value pairs within the browser of the user. So you can simply use the local storage, which is one sub storage. There's also the session storage, and you can use local storage to simply say store the value bar under the key foo. Then you can close the website, you can close the browser. Weeks later, you can open the browser again, go to the same website, and then the same website can do local storage get item, and then provide this key foo here, and it will receive the value bar in its test variable. So this is a way how data can be stored in local storage, and the local storage strictly adheres to the same origin policy. So each website gets an own storage area assigned to it, each origin even. So one website is not able to access data of another website. And therefore, let's have a look at the score again, and I guess this round also clearly goes to the HTML5 web storage API. Okay, so now we covered a few functionalities that are used by applications to provide certain use, or to create certain use cases, or to implement certain use cases. And now I would like to also talk about specific security features. So normally I would like to talk about two things, about clickjacking and about cross-site scripting, but I left out cross-site scripting because of timing reasons. So we will only talk about clickjacking protection. And we'll first have a look at what clickjacking is and how legacy protections against clickjacking work. So clickjacking or UI redressing is an attack where an attacker tries to steal clicks of a user. And how this works is the following. So an attacker has its website, evil.com, and what he does is he frames a site he wants to attack within an iframe. Then he somehow hides the iframe, for example, by making it invisible, by making it very small, only 1 pixel large, or by covering with other elements. And then he somehow tricks the user into clicking on his website. And shortly before clicks arrive, the attacker moves the iframe under the mouse of the user. And then the user clicks, and instead of clicking on the attacker's page, the click goes to the hidden iframe. And therefore it clicks some elements on the hidden iframe. And if you have your administration panel of your website and there is a delete the whole application button and you hit it, you might be deleting your application without wanting it. And a legacy protection that is used to counter such threats are JavaScript frame busters. So the idea is that we would like to prevent this first step, this framing cross-domain content. And we can see a very naive and broken implementation here. So here we simply have a small JavaScript, and in this JavaScript we check if the parent frame is different from the own frame. And if we are not framed, this is the same, so the check will not be executed. But if we are framed, the parent is different from our own frame, and therefore a redirect is conducted from parent location to self location. So basically, we redirect the top frame or the side that frames us to our own location, and effectively busting out of the frame and loading our page as the main page. And this JavaScript implementation is seriously flawed because there are a lot of different ways to circumvent it. So basically there are two ways. The first way is to prevent the JavaScript from executing. So one attack that was used was misusing cross-site scripting filters. So cross-site scripting filters sometimes deactivate certain JavaScripts if they think they are injected by an evil attacker. So what an attacker does is he puts the framebuster into the URL. That this makes the cross-site scripting filter think this framebuster is injected and says, well, I deactivate this. This might be an attack. And then the framebuster does not run, and you can frame the site and do your click-checking thing. The second technique to prevent JavaScript execution was using HTML5 sandboxed iframes. So in sandboxed iframes, a way to somehow sandbox content, for example, provided by user, and you can use a frame and say, well, this is sandbox, don't execute JavaScript in this frame. And then the framebuster is not executed, and again, you can conduct your click-checking attack. And the second possibility that you can do is you can prevent the redirect. So in this case, in this framebuster here, we see there is a redirect happening. And there are 3 different techniques how we can stop redirects in a browser. The one is quite interesting, the 204 flushing. It was simply an attacker can basically flush the buffer that the browser has to store all the redirects that he can do by sending a lot of 204s. So 204 is an HTTP response code that says basically says do nothing. So the attacker conducted a lot of 204s. The browser does a lot of requests, but always does nothing. And then somehow forgot that he needs to redirect this page where the framebuster is on. And then there are other techniques like double framing, or you can simply ask the user nicely. So you can simply ask, would you really like to leave this website? And if the user presses no, the redirect is canceled. So this JavaScript implementation is really flawed that we saw here. And there are ways to create secure framebusters, but the knowledge about this is not very widespread. And most of the framebusters look like this one, and not like secure ones. So let's look at the HTML5 way of doing this. And here we use the buzzword HTML5. So X-frame options is not really an HTML5 feature, but we say HTML5 is everything that is new within the browsers. And X-frame options is an approach that was introduced by Microsoft. And this is an HTTP response header that you can specify for a page. And in this HTTP response header, you can specify whether a page is allowed to be framed or not. And if a browser receives such a page that has such a header attached to it, it will enforce the behavior that you specified. So if you say framing is forbidden, the browser won't frame this page at all, but simply show a wide empty page. And the big advantage is that this is not a JavaScript solution, so you do not have to rely on certain properties of the language, or you do not have to rely that JavaScript is actually activated, and therefore it's much harder to circumvent. So therefore, let's look at the score again. I think here also the X-frame options header wins, and therefore it's 4-0 for HTML5. So now let me shortly draw a conclusion. So what we saw in this talk is that modern browser features are not there for fun. They are there for a reason. So thought about it, and there were needs by developers that preceded them. And these modern browser APIs were introduced to realize certain cases, which were already realized before, but with a much better security model in mind. So the JavaScript solution and the hacks that we just saw, they do not have a security model at all. At least Flash has one, but it's also not very good. And these APIs are, for the first time, really designed with security in mind. And therefore, they are not as bad as their preconception might be. And often, they are even superior on a functional level. So they can do more, and they can store more data, or give finer access control than the legacy features. With this, I would like to thank you for your attention. And if you have any questions, you are free to ask. Yes?
Regarding the comparison by cookies.
Yes, you can protect the cookie with the HTTP only flags, but only against a web attacker. For example, you cannot protect the cookie against a network attacker that is in your network. He will still be able to read it. And yeah, cross-site scripting for local storage is a problem, and you should somehow protect against it. And yeah, but there is no real good solution. But local storage is much better suited for storing data than for cookies. Cookies are not made for storing data and are not made for storing sensitive data. But local storage is made for data at least. And if you store sensitive data, you should have some kind of policy. And you can also extend local storage to have certain security properties. So if you like to have encryption, so we thought the JavaScript encryption talk a few hours ago, you can use this much better than with cookies. Other questions? Yes? Okay.
By using HTTP only flag, you by definition, by its user, you can no longer use cookies to store browser because you cannot query.
Yeah, sure. Yeah, of course.
Really, it doesn't make sense.
Yeah, of course. Yeah, sure.
Can you just repeat that?
Yeah, the comment was that if you use the HTTP only flag, and that's correct, that you cannot access the data anymore on the client side. So if you want to process it on the client side, you have a problem. Other questions? Okay, then thank you very much.